Hello friends. So previously we have studied what is finite state machine, what is its definition, what are the two types of function it has. In this video we are going to study the problems on finite state machines, which are basically classified into three types. With this we are going to start with the type 1 problems. Now the type 1 problem that we have says, the problem definition is, let me write it. Now you have to more of observe the screen and listen to me. So the question over here says, type 1 problem number 1. Question over here says, design a FSM to check whether the given decimal number is divisible by 3. So this problem comes in the exam for 5 to 8 marks. So coming on to solving this problem, the step number 1 in solving this problem will be a very monotonous step that you will be supposed to write again and again, and that step is called as the theory. So my step number 1 will be the theory. By theory I mean we are going to write the formal definition of finite state machine. FSM consists of finite set of states S which alter on receiving the input set I to produce the output set O. It consists of two functions, state function and machine function, wherein the state function says given a state and an input what is the next state, and the machine function says given a state and an input what is the output. So these all things have to be come into the theory part. This will account to approximately 1 mark in your exam. Moving on to step number 2. Now my step number 2 is a step wherein we decide the logic of the problem. Now when I come to the logic of the problem, the first and foremost thing which comes to mind is to understand the problem. Now what is the problem exactly saying? The problem says design a FSM to check whether a given decimal number is divisible by 3. Now if I am talking of a decimal number, first and foremost thing, what is exactly a decimal number? A decimal number is a number which is formed by picking up any of the digits from 0 to 9. So if I pick up any of the digits from a set of 0 to 9 and form a random number, that number will be called as a decimal number. So can I say number 999 is a decimal number? Yes. Can I say 1999 is a decimal number? Yes. Can I say 19990 is a decimal number? Is this a decimal number or is this a decimal number? Yes, of course this is a decimal number. Why? Because it is formed from picking up any of the digits from 0 to 9, right? So the question over here says we have to find out whether this particular number which is given, is it divisible by 3? Rather, to be specific, not this number, any decimal number. If it is divisible by 3, you tell me yes, it is divisible by 3. If it is not divisible by 3, you say no, the machine is not able to divide the number. So it is not a divisible by 3 number. So the output of the machine over here is either going to be yes or no. Okay, so let's start with this step. So what it says, the definition says given a state and an input, what is the output? So let me write all those three things. The states over there will called as the S, the input over there was called as the I, and the output over there was called as the O. Now when I talk of output, I just now said the machine has to tell me whether a number is divisible or not divisible. So can I say the output is going to be kind of boolean, yes or no? So I say the output set over here is going to consist of either yes or no. You have to include it inside the brace brackets. Okay, so that is my output set. Next I come across will be called as the input set. Input set 2, we just discussed that. When I talk of a decimal number, what is the decimal number going to comprise of? It is going to comprise of all the numbers which are either 0, 1, 2 or 9 combination. So any combination of the numbers picked up from this set is going to form me a decimal number. That exactly what is my input set. So input set says you pick up any of the number from this particular set which is 0, 1, 2, 3, 4, 5. 6, 7, 8 and 9. Any number you pick up from this particular set and you form a number, that number will be called as a decimal number. So that is basically my step number 2. Now you can see there is one more thing which I have left blank over here, which is called as the states. At this stage we cannot fill in the number of the states. We will be coming back to this point later. For now, let us move ahead and go to my step number 3. Now my step number 3 is the implementation step. Rather, I would say it is going to be the heart of the problem. If you understand step number 3, all the other steps are going to be cakewalk for you. But provided you understand step number 3 in detail. So let's start with it. So my step number 3, I call it as implementation. Okay. Now, whenever I talk of implementation, we just now discussed that there are going to be two functions, state function and a machine function. Now, machine function is going to be really easy. The first foremost thing that we should understand is the state function. So, let me show you how a state function is populated. So, a state function is basically going to be a tabular representation of some states across some inputs. So, that's how we write it. So, we have STF as my state function, which says given a state and an input, what is the next state. So, we write it in the tabular fashion, given a state across some inputs. Okay. Now, coming on to this particular problem, you can see the state function is demanding me for two things. The first one is called as the states, which you can see over here, and the next one is called as the inputs. Let's initially fill the inputs part. When I talk of the inputs, we all know the inputs which are going to be possible from this is going to be 0, 1 to 9. So let us write it over here. I have 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. Let us complete this table first. So I have a state for 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Now every time I talk of a particular machine, assume you are sitting in front of a computer and you are starting your computer. When the computer initially starts, it is currently in a steady state. That is, it is just waiting for some kind of input, maybe a mouse click, maybe a keyboard click, maybe starting a web camera or any other operation. Similarly, when I talk of a finite state machine, our finite state machine currently is in a state which is called as a start state. When I talk of start state, in TCS, the states are usually abbreviated by the symbol Q. So, the machine by default always when started will be in a state which will be called as the start state, and start state is denoted as QS. Also, the start state is denoted by a special symbol which is this arrow symbol. So, don't forget to mark this arrow symbol. QS is a start state, therefore it is denoted by an arrow symbol. That's it. Fine. So, when the machine starts, it will be going into the start state. Now, coming on to what are the different other type of states that it can encounter. When I talk of a number which is going to be divisible by 3, how can we categorize the number into different categories? For example, if I want to know whether a number is divisible by 3, let us take a very simple example. Let me say I have a number called as 0. Is my 0 divisible by 3? How do you find out that? I say, why not divide the number 0 by 3 and check. So when I say what is 0 divided by 3, so you will say the quotient is going to be 0, right? But I am not interested in the quotient. Rather, it will be more advisable to look into the remainder part. So I say what is going to be 0 mod 3? 0 mod 3 will be 0, fine. What is going to be 1 mod 3? 1 mod 3 is going to be the remainder when 1 divided by 3 comes out to be 1. What is going to be 2 mod 3? 2 mod 3 is going to give me the remainder as 2. So basically I am going to keep a track of my remainders in my RHS. So I say all my remainders are going to be kept a track of over here. Now let me consider one more number. If I take a number like 3, What is going to be 3 modulo 3? 3 modulo 3, I think it is going to give you a remainder as 0. What is going to be 4 modulo 3? 4 modulo 3 is also going to give a remainder as not 0, it will be giving a remainder as 1. 5 modulo 3 is going to give a remainder as 2. 6 modulo 3 is again going to give a remainder as 0. So if I populate the gist of all these things, can I say a number like 0 or 3 or 6 or 9, so on and so forth up to infinity, when divided by 3 is going to give me a remainder as 0? Yes. Can I say the numbers like 1, 4, 7, 10 when divided by 3 is going to give me a remainder as 1? Yes. Similarly, the numbers like 2, 5, 8, 11, all those numbers when divided by 3 are going to give me the remainder as 2, right? So if I abbreviate all these entire sets, I see that the only possible remainders when a number is going to be divided by 3 is going to be either 0 or 1 or 2, right? That are exactly the states which I was looking for in the problem. So when I talk of checking whether a number is divisible by 3, I am very sure, as I compared with the lift example. So here we have got 3 distinct states, and those states are 0, 1 and 2, right? So coming back to our slide. So let me write the states over here in our state function. So we have to keep a track of the remainders, which can be either 0 or it can be 1, it can be 2. So looking over here, I can see that I have a total of 4 states with me. One is the start state and another 3 states which are going to keep a track of the 3 possible remainders, right? Now how are you going to label those 3 states? The first state will be labeled as Q0. So let me write it as Q0. The second state will be labeled as Q1, the third state will be labeled as Q2. Frankly speaking, there is no compulsion as to, frankly speaking, there is no compulsion. You can label it by any name you want. You can label it as A, B, C, D, you can label it as X, Y, Z. But the popular conventions used in the book, used in the paper, used by many of the proper available trainers is Q. Therefore, we are also going to use the same so that we are in sync with the subject. So we have a possible number of states over here as 4. They are basically QS, Q0, Q1, Q2. By now I am very sure you must have understood what I mean by states. Can a number when divided by 3 land in any other than these 4 states? No. Right? So a number can be either divisible by 3 or it cannot be divisible by 3. And if it is divisible by 3, the remainder can be either 0 or 1 or 2. That's it. Fine. So with this, we go back to our step number 2 where we have left the state set empty. So in the state set now I can say I have total of states which is namely QS, Q0, Q1 and Q2. So that completes my step number 2. Coming back to step number 3 in the implementation. In implementation, so now we are clear. In the column side, we are going to have the states QS, Q0, Q1, Q2, and along the rows, the values that are going to be filled are going to be of the various inputs. Okay. Now, if you look at the problem, initially, as I told you, the machine is always going to be in the start state. By start state, what do we understand? The machine has just been turned on. It is very much possible that when the machine has been turned on, have you given any kind of number to that machine as input? No. So over here, the machine is actually in the idle state and it is not getting any kind of input. It is just in a idle state waiting for the input. So if you observe this particular state, which I am currently highlighting with the marker, this state over here, what we are going to say, the machine is currently in the start state and it is going to receive some kind of input. Over here the input is called as a 0. Abbreviating, I again say, if you recall the state function, what was the state function saying? Given a state and an input symbol, what is the next state? Here we are exactly trying to figure out the same thing. What I say over here is, given a state QS and an input symbol 0, what is going to be my next state? I repeat, given a state QS and an input symbol 0, what is going to be my next state? So the machine currently is in the start state, machine does not have any kind of input. Now what happens over here is the machine is in QS and the machine receives an input called as 0. Now you tell me, when a number 0 is going to be divided by 3, what is the remainder that it can achieve? 0 when divided by 3, the remainder over here is going to be 0, right? Now if you observe the remainders in the state transition function, which of the state has a remainder 0 associated with it? I can see that state number Q0 has a remainder 0 associated with it. Therefore, the machine in the start state, when receives an input symbol 0, when divided by 3 is going to give remainder as 0, and that remainder 0 is belonging to the state Q0, and therefore the machine goes to state Q0. Similarly, when I talk of filling this next important thing, which is called as transition on receiving the input symbol 1, now we are not going to assume that the machine already has something. Every time a finite machine is going to execute, it will assume that it is running with no previous knowledge. So I assume that the machine is again in state QS, it does not have knowledge of anything, it has just started and it has received an input symbol 1. So the machine does not have anything, it receives 1. So the number which the machine has right now is 1. 1 when divided by 3 gives the remainder as 1. And remainder 1 belongs to which state? Remainder 1 belongs to Q1 state. And therefore Q1 is going to be filled over here. How do we read that? We say over here, QS on receiving an input set I produces an output set Q1. Or rather, in another way we can say, QS on receiving 1 goes to Q1. Similarly, QS on receiving 0 goes to Q0. So that's how my state function works. Once again, filling it in the same manner, the machine does not have anything with us. The machine receives an input symbol 2. 2 when divided by 3 gives the remainder as 2. Remainder as 2 means it will be going to the state Q2. Going ahead, the machine is again in state QS and the machine receives an input symbol 3. So 3 when divided by 3 gives the remainder as 0, and remainder 0 is nothing but state Q0. Therefore machine goes back to the state Q0. Similarly, QS on receiving the input symbol 4. So the number becomes 4. 4 when divided by 3 gives the remainder as 1. Remainder as 1 means it will be going to state Q1. That's also one more reason why I have taken the state names in sync with the remainders. So it will be easy for us to map. You can see over here, remainder 0 state Q0, remainder 1 state Q1, remainder 2 state Q2, so on and so forth. Similarly, I am in state QS. The machine receives an input set number 5. 5 when divided by 3 gives the remainder as 2. Remainder as 2 means the machine will be going to state Q2. QS on receiving input number 6 when divided by 3, 6 divided by 3 gives me remainder 0, therefore I go to state Q0. Similarly, QS on receiving 7, 7 divided by 3 gives me the remainder 7 divided by 3, 3 2s are 6, remainder 1 means Q1. Similarly, QS when receives an input number 8, 8 divided by 3 is going to give me the remainder as 8 divided by 3 2s are 6, remainder as 2. So it will be going to the state Q2. Did you observe one interesting thing over here? The pattern which we have generated. If you observe, initially in the QS row we have Q0, Q1, Q2, again followed by Q0, Q1, Q2, again followed by Q0, Q1, Q2. So by now you should be in a position to guess what is going to come in the ninth column. Ninth column says QS on receiving number 9. 9 when divided by 3 gives the remainder 0 and it has to be going to the state Q0. You can observe over here that the pattern is getting repeated, and this pattern is going to repeat in the lower part of the problem again. But the solving the lower part of the problem is going to be somewhat tricky. Because in the start state we did not have anything, we actually need not bother of a lot of the background scenarios. Whereas when I talk of the states which are going to come beneath that, they have some kind of history associated with them. So let's go on to our state number Q0 and understand what is the history associated with state Q0. Now if I talk of the state Q0, I just told you that Q0 is a state which is going to keep a track of all the numbers that are going to give the remainder as 0. So can I say in Q0 state a number like 0 belongs, a number like 3 belongs, 6 belongs, 9 belongs, 12 belongs, dot 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 up to infinity. So any of the number in this particular set belongs to set Q0. That is, all these numbers are valid because these numbers when divided by 3 give remainder as 0. Similarly, if I talk of state Q1 which is going to give me a remainder 1, the numbers which belong to this set are 1, 4, 7, 10, 13 up to infinity. And similarly for state Q2 where the remainder is 2, the numbers are 2, 5, 8, 11, 14 up to infinity. So from now when I say I am talking of a state Q0, you should understand that Q0 is such a state which is going to hold a remainder 0 numbers. That is, the numbers 0, 3, 6, 9, all such kind of numbers will be in Q0. The numbers like 1, 4, 7, 10, 13 will be belonging to state Q1. And the numbers like 2, 5, 8, 11, 14 will be belonging to the state Q2. So let me quickly write the numbers which belong. Can I say the numbers which belong to Q0 are 0, 3, 6, 9, so on and so forth. Similarly, over here we have 1, 4, 7, so on and so forth. We have 2, 5, 8, so on and so forth. So coming on to the state Q0, as I told you, Q0 can hold the numbers like 0, 3, 6, 9. So we can actually consider any of the numbers. For simplicity, right now I am considering that Q0 is currently holding, it is just an assumption, Q0 is currently holding a number 0. Let me write the number over here. So the number is 0. Now Q0 is currently holding a number 0 and what comes as input is another number called as 0. So 0 appended with another 0, the number becomes 0, 0. 0, 0 is again nothing but 0. So when 0 is divided by 3, what is the remainder that we get? 0 divided by 3, remainder 0. What is the state storing a number with remainder 0? Q0. Therefore, Q0 will be replicated over here. Similarly, instead of assuming a number initially from this set as 0, I say I assume another number called as 3. So I am assuming in state Q0 there was initially a number called as 3. So 3 was initially there and what came after that in the input was 0. So the number became 30. 30 when divided by 3 again is going to give me the remainder as 0. Remainder as 0 means I have to go to Q0 and you can see over here that Q0 is already there. Assume any other number. Let's say you assume a number from this set like 12. So you have currently 12 with you in state Q0 and the input like 0 comes. Number becomes 120. 120 again when divided by 3 is going to give you the remainder 0. So what I want to convince you over here is you assume any number from this particular set. It is always going to say go to state Q0. So now let us go ahead and start filling the next cells. So if you observe, I am currently talking of cell Q0 and Q0 when receives the input symbol 1, what is going to happen? Q0 initially had a number like 0, it received input 1, the number became 1. 1 when divided by 3 gives a remainder as 1. Remainder as 1 means it has to go to state Q1. Similarly, when I talk of filling this particular cell, Q0 I am assuming already has a number like 0. 0 when come across with a number like 2, the number becomes 0, 2 which is nothing but 2 again. When divided by 3, it gives the remainder as 2. So it goes to state Q2. Now for the purpose of simplicity, from this particular set, I am always going to select 0. The reason being, I take any number from this set, the state which it finally going to land is going to remain the same. So let us keep it simple by considering the smallest of the number, that is going to reduce our time in the calculations. Therefore, I say over here, going ahead with the next cell, I am currently in state Q0. So assuming I have 0 with me and the number which I encounter is 3 and 3 when divided by 3 is going to give me the remainder 0. So remainder 0 means it is going to go to state Q0. Did you again observe some pattern over here? I can see Q0, Q1, Q2, Q0. So just like the above row, do I see the same patterns getting repeated again? Yes, you are right. And it will always be repeated for 95% of the times. Also, it will be repeated exactly as it is in the above row. Meaningly, I want to say that if you observe all the states or all the rows of QS, I see that it is Q0, Q1, Q2 dot dot dot. It is exactly identical to whatever we have currently filled in state Q0. And that's not a coincidence. It is always going to be same. So QS and Q0 are always going to be same. So for now, I'll just fill up all the rows, all the values, and let us verify some of the cells. So this will be Q1, this will be Q2, Q0, Q1, Q2, Q0. Now let's say I am planning of verifying this particular cell which I just circled right now. In for this particular cell, I say I am in a state Q0, that means I have a number like 0 with me, and what came to me was 5. 5 when divided by 3 is going to give me remainder as 2. Remainder 2 means I have to go to a state Q2, that's exactly what we have. Similarly, you can also verify with all the values that I have just filled of the states, and they are of course going to be the same. Now moving on to the next row. In the next row, we are coming to state Q1. Now Q1 is going to store all the numbers like 1, 4, 5, 7 dot dot dot. Again for simplicity, we are going to assume 1. Now in Q1, the number currently which I have with me is 1. Now 1 I had with me, and Q1 currently receives the input symbol 0, and therefore the number now for the first time becomes 10. 1 when appended with 0 becomes 10. So 10 when divided by 3, the remainder which I get is 1. What is the remainder 1 state? Remainder's 1 state is nothing but Q1. Therefore, I write Q1 over here. Let's repeat the same thing. I have 1 with me, and Q1 now encounters a 1. So the number becomes 11, and 11 when divided by 3 gives me the remainder as 2, and it goes to state Q2. Similarly, I repeat the same thing for 2. I have a number like 1 with me, and what it encounters right now is 2. So the number becomes 12. When modulo 3 is going to give me the remainder as 0. Therefore, remainder 0 state is Q0. By now, I am very sure you might have again guessed that there is some kind of pattern which is going to get repeated. We'll observe this once again. So let us say I am currently in Q1, therefore I have 1 with me. What I encounter over here is a 3, that makes my number as 13. 13 when divided by 3 gives me the remainder as 1. So remainder as 1 means I will be coming across Q1. So did you observe the pattern Q1, Q2, Q0, Q1, Q2, Q0 getting repeated? Yes. And that's why I'm going to directly fill it. So I say Q1, Q2, Q0, Q1, Q2, Q0, again followed by Q1, right? You can also verify. Let's say we are considering verification of this particular cell. So what I had with me was 1. What came across was 6. Number became 16. 16 when divided by 3 gives me remainder 1, and that is exactly Q1. So that's how we filled our first Q1 state. Now coming on to the last Q2 state. Now in Q2 state, we are going to have set of all the numbers which when divided by 3 are going to give the remainder as 0, which is exactly what we listed over here, 2, 5, 8, 12 dot dot dot. So for simplicity, as I told you, we are going to assume the easiest of the number 2. So in Q2 state, I have a number like 2, and 0 comes across, number becomes 20. 20 when divided by 3 gives the remainder 3 6 18, remainder as 2. Remainder 2 means I have to go to Q2 state. Therefore, I write Q2 over here. Similarly, for filling up of this cell, I assume I have 2 with me. What comes across over here is 1. 21 when divided by 3 gives me remainder 0. Therefore, I go to state Q0. Similarly, for filling up of this, again I assume I have 2 with me, and I come across a number like 2. So 22 when divided by 3 gives the remainder as 1, and I go to state Q1. As you saw in all the above rows, there was a pattern which was followed, and that turned out to be right. Similarly, the pattern that we are going to have over here in the row Q2 is Q2, Q0, Q1 in a repetitive fashion, and that is also by default going to be right. So therefore, I rewrite it over here again: Q2, Q1, Q0, Q2, Q1, Q0 followed by Q2, right? So now what I prepared right now was called as a state transition table. Please don't focus on understanding how the problem is going to be get solved, because that will be clear by the time we complete the entire problem. As of now, what is important is you understand the working of this particular procedure. So with this, we complete the state transition function. Now, did you observe some kind of peculiarity in the state transition function? For clarity, I will just highlight some of the things. So if I observe this first row of first column of 0th value, I see Q0, Q0, Q1, Q2. Similarly, can I observe the same value in this third column also? Q0, Q0, Q1, Q2. Similarly, did you observe the same thing in the sixth column also? Q0, Q0, Q1, Q2. And also the same peculiarity can be seen in the ninth column. Can you see all these highlighted cells? Yes. Let's go ahead and observe some kind of peculiarity in further more columns. If I observe my column number 1, which consists of Q1, Q1, Q2, Q0, when compared with column number 4, which again consists of Q1, Q1, Q2, Q0, coming on to column number 7, which also consists of Q1, Q1, Q2, Q0, they also turn out to be exactly the same. Similarly, you can observe the same thing for my second column. Second column says Q2, Q2, Q0, Q1. Fifth column says Q2, Q2, Q0, Q1, and eighth column says Q2, Q2, Q0, Q1. So I can see that the columns are basically broadly categorized into three types. What are those three types? Can I say the columns 0, 3, 6 and 9 can be clubbed together? Yes. Can I say the columns 1, 4 and 7 be clubbed together? Yes. Similarly, can I say the columns 2, 5 and 8 also be clubbed together? Yes. So I can actually make a summarized table of all these columns side by side. Okay. With this, I'll just modify this table and show it to you. So with this, we can see that the whole big table was now abbreviated or shortened to a very small length, and it makes actually more sense to make the table in this fashion by realizing how the table can be shortened right at the start of the problem, rather than doing the entire work and then scribbling up and again coming back to this table. So advisably, for solving all the further problems, we are going to club the states, club the inputs together and then solve the problems. So with this, I say my state function is ready with me. But if you remember, there are total two functions to be implemented in this problem. The first is state function and the next is machine function. But if you have understood this particular function, right now you can consider the problem to be solved. You are good to go to solve the further part of the problem, because that is now going to be a cakewalk. So without wasting time, let's go to the machine function. So how do we define a machine function? A machine function is defined by MAF. It basically says, given a state and an input, what is the output? So let's draw the table. I again write S cross I over here. The inputs over here are 0, 3, 6, 9. Similarly, over here we have 1, 4, 7, and over here we have 2, 5, 8. Fair enough. Here also we have the states QS, Q0, Q1, Q2. Of course, they are not going to change because we are talking of the same machine. Now, one more important thing that you have to understand. The start state is always denoted by an arrow and the final state will always be denoted by a star mark. What do I mean by that? When do I say a number is divisible by 3? When the remainder is 0. And what is that state which is holding all the numbers with remainder 0? It is nothing but the state Q2. Therefore, I say mark Q2 as the final state in both the diagrams. Therefore, I say Q2 will be marked with a star over here, Q2 will be marked with a star over here. Going ahead, now since Q2 is the final state, observe in the state transition function which all cells correspond to the cell or correspond to the cell value as Q2. I can see the following cells with cell value Q2. The first one I observe is this. Since this is Q2, in the corresponding column I write yes, because my output function was saying given a state and an input, tell me whether the number is divisible by 3 or not. So I write yes over here. Similarly, here I again write yes because this Q2 is corresponding over here. For this Q2 I write over here yes, and for this Q2 I write over here yes. That means these all are the cell values where the input is going to take us into a final state. Other than that, all of them will be talked as the non-final states. So I will say if the machine goes in any of the states other than this, the number is not divisible by 3. Therefore, write no in all the remaining cell entries. So I write over here no, 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 and no. That completes my machine function, right? So we are done with the state function, we are done with the machine function. Now we are left with very small thing, which is nothing but my step number 4 and step number 5. Now step number 4 is called as the transition state or transition diagram or transition graph. Let us write it. So we have our step number 4, which we called as transition diagram, or sometimes it is also called as a transition graph. So the transition diagram will be a graphical representation of what is done in the step number 3. So coming on to step number 3, if you observe over here, can I say QS on receiving input symbol 0369 is going to state Q0? That's how you read the state function. QS on receiving either 0 or 3 or 6 or 9 goes to Q0. QS on receiving either 1 or 4 or 7 goes to Q1, so on and so forth. Similarly for machine function, how do you read it? QS on receiving 0, 3, 6 or 9 gives the output as no. QS on receiving input 1, 4, 7 gives the output as no. Similarly, if you consider Q2, Q2 on receiving 0, 3, 6, 9 gives the output as yes. That's how you read the machine function. So we are going to translate this entire table into a graphical representation. How? By writing all the states in a graphical form. So what are the different states that we have? QS, Q0, Q1, Q2. So let us write it in the step number 4. I have state QS. Since it is a state, transition diagram says put it in a form of circle. Then I have Q0, then I have Q1, and I also have Q2. Now what is the start state? We all know the start state is QS, and in transition diagram the start state is also denoted by an arrow symbol, and the final state is Q2. Don't put a star over here. We have to enclose the final state in double circle. That's how transition diagram depicts it. So now if I move on to step number 3, I see that QS on receiving input symbol 0369 goes to state Q0. I repeat, QS on receiving input 0369 goes to state Q0. Okay, so I say QS is going to state Q0, therefore I draw arrow over here. But when does it go to Q0? On receiving input 0, 3, 6 or 9. Okay, come to step number 3 again. QS on receiving input 0369 goes to state Q0 and the corresponding output which it gives in state Q0 is no. So make sure you mark it. So the corresponding output which it gives over here is no, right? Similarly, go ahead. I have QS on receiving input 147 goes to Q1 and gives the output as no. So QS on receiving input 147 goes to Q1. So QS on receiving input 147 goes to Q1 and gives the output as no. Similarly, QS on receiving 258 goes to Q2 and gives the output as yes. So QS on receiving input 258 goes to Q2 and gives the output as no. Similarly, QS on receiving input 258 goes to Q2 and gives the output as yes. So QS is going to Q2 on receiving input 258 and the output which it gives is yes. Similarly, we are going to fill the entire diagram. So let's now go on in a bit faster manner. I say Q0 again goes to Q0. Okay, so Q0 is going to Q0 where I'm talking of this particular part. Q0 on receiving 0369 goes to Q0 and gives output as no. So Q0 on receiving input like 0369 goes to Q0 and gives the output as no. Similarly, Q0 on receiving 147 goes to Q1 and gives the output as no. So Q0 on receiving input 147 goes to this and gives the output as no. The next is Q0 on receiving 258 goes to Q2 and gives the output as yes. So Q0 on receiving input 258 goes to this and gives the output as yes. Did you observe an interesting thing over here? All the arrows which are going inside the Q2 circle are giving the output as yes, and anything which is going outside of Q2 or to any other states, they are giving the output as no. And of course, that's how it has to behave. So let's go ahead. I feel the same thing for Q1 and Q2 now. So now you can see that I have completed the transition diagram. Don't bother about the colors. I have just made it in different colors because I wanted to show you that these all things are distinct. Although they are part of the same thing, this is actually done only for increasing the readability of the user. Fine. So that actually completes my step number 4, which is nothing but the implementation of transition diagram or the transition graph. With this, we are going on to the last step, which is called as the examples. So let's go ahead. So my step number 5 is examples. So let us consider the very first example. Now what is the reason that we are going for example? The reason is, when we have implemented such a big logic, don't you think that whatever I have taught you should work? So for confirming whether your answer is right or wrong, examples are the best way to check. So our machine was basically interested in finding out whether the number, which is the decimal number, is divisible by 3 or not. So let's assume a decimal number which is divisible by 3. So let me take a number like 3612. So 3612 is divisible by 3. First let us check. So 3612 when divided by 3, that is 1, this gives me 2, this gives me 0, and 3 4s are 12. Yes, the number is divisible. So let us start and check, is the machine capable of doing the same thing? Of course, that's the reason we have built it. So let's start with it. Initially the machine is in state QS, so I write QS. The input which I have over here is 3612. Now what does FSM say? The input is going to be read character by character. Over here it will be digit by digit. So what am I trying to say over here is, QS on receiving a input symbol 3, what is happening? Tell me. So if I go to my transition function or the implementation, I see over here that QS on receiving a input symbol 3 is going to take me to a state Q0. So let us do that. QS on receiving input symbol 3 is going to the state Q0. What is pending with me is 612. What is the symbol now? This symbol is nothing but signifying that we are going to have a transition effect. That is, we have read one input and we are now going ahead to read the next input. So let's go ahead in the same fashion. Now I come across Q0 on receiving an input symbol 6. Let's go back to that implementation and check. QS on receiving 6 is again going to Q0. So right over here Q0. What is left with me is just 1 2. Okay. Now what is Q0 on receiving input symbol 1, go back to the implementation. QS on receiving 1, it is going to the state Q1. Okay, so QS on receiving 1, it is going to the state Q1, and what is left with me is number 2. Now, what is Q1 on receiving the input symbol 2? Let us check. Q1 on receiving the input symbol 2 is going to take me to a state Q0. Okay, let's write it first. It is going to take me to a state Q0. Do I have any other input now? No. Since the input scanning is finished, now it is the time to finally look into the machine function and check whether the number is accepted or rejected. So what was the last thing that we read? Q1 on receiving 2. So let's go to the implementation and check. When I say Q1 on receiving number 2, it is going to give me output Q0. What was the corresponding output for Q0? The corresponding output for Q0 was yes. Since the corresponding output for Q0 was yes, the number is going to be accepted. So the corresponding output will be accepted. So here it is going to be no, and here it is going to be yes, because it is signifying actually yes to this and no is signifying to this. Fine. So since the corresponding output over here is yes, we say this number will be accepted by the finite state machine. So that shows me that when a number is taken and divided by 3, this machine is accepting it. But let's also consider the vice versa scenario to check whether a number which is actually not divisible by 3 and check whether the machine is also rejecting it. So let us consider another example. The example says QS on, let us say the number be 3192. So 3, 4, 9, 13, 14, 15, and let us take 1 over here. Fine. So I know that the number 31921 is not divisible by 3. Let us check whether the machine does it. So what is QS on receiving input symbol 3? QS on receiving 3 goes to Q0. So I say goes to Q0, pending is 1921. Q0 on receiving 1, Q0 on receiving 1 goes to Q1. So let's write over here Q1, remaining is 921. What is Q1 on receiving 9? Q1 when receiving input 9 goes to Q1 again. So write Q1, pending is 21. What is Q1 on receiving 2? Q1 on receiving input symbol 2 is Q2. So I say go to Q2, pending is 1. What is Q2 on receiving 1? Q2 on receiving 1 is going to give me Q0. Q0. Just check in your transition function. Is Q0 the final state? No. The final state is Q2. Correspondingly, you can also check the entry of Q0 in the machine function. It is also saying as no. Since it is no, I say the number is going to be rejected. So this actually confirms that a number will be accepted or rejected by a FSM which we implemented is working perfectly fine. So this is how we solve a finite state machine problem, wherein we are basically helping a machine understand, or we are trying to understand how a machine interprets whenever I give a high level program to the compiler and make him understand what is going to be the logic of it. That's how it performs. So with this we can say that we have successfully completed the problem 1 type 1. In the next video we will be starting with the remaining problems. Thank you everyone.